Hey everyone, and welcome to another explainer right here on my channel, JEE Concept Galaxy. Today, we are diving headfirst into one of the absolute coolest detective stories in all of science, how humanity finally unlocked the structure of the atom. It's this wild journey full of brilliant insights, total accidents, and moments where the absolute smartest people on Earth realized that everything they knew about atomic models was just completely wrong. It's going to be a fun one, so if you enjoy this kind of deep dive, make sure to like, share, and subscribe. All right, let's just jump right in.
So let's start with a really profound question. We're taught that atoms are made of positively charged protons and negatively charged electrons, right? And basic physics tells us that opposites attract. So why don't the minus charges just pull right into the plus charges and crash? Why doesn't all matter everywhere just immediately collapse into a microscopic speck of nothingness? Well, answering this seemingly basic question actually required a complete, from-the-ground-up rewrite of the fundamental laws of physics.
Here's our roadmap for today's explainer. We're going to cover 1. The plum pudding model, 2. Rutherford's gold foil surprise, 3. The collapsing atom paradox, 4. Bohr's quantum leap, and finally, 5. The quantum mechanical cloud.
To give us kind of a mental map of this journey, take a quick look at this timeline. Think of this whole history as a giant scientific relay race. One scientist solves a huge problem, hands off the baton, but oops, they accidentally create an entirely new, even worse problem for the next person. Notice how fast this all happened, too. We go from J.J. Thomson's model in 1898 to a full-blown quantum revolution by 1926. In less than 30 years, our entire conception of reality was completely turned upside down.
Okay, first stop on our timeline, Section 1, the plum pudding model. So back in 1898, scientists knew the atom had to be electrically neutral, but they also knew it had these negatively charged pieces inside it, what we now call electrons. So how did J.J. Thomson picture this? Well, he thought the atom was basically a spherical, positive cloud with negative electrons just kind of stuck randomly inside it. People called it the plum pudding model, but honestly, a watermelon is a way better analogy. Picture the red, fleshy part of a watermelon as this solid, positive sphere, and the black seeds scattered inside are your negative electrons. It was actually a really elegant way to explain a neutral atom, and it worked perfectly to explain why heating up metals made them spit out negative charges. But then, we get to Section 2, Rutherford's gold foil surprise.
In science, neat and tidy ideas like the watermelon model rarely last very long. In 1911, Ernest Rutherford and his team decided to put Thomson's model to the test. They fired a beam of heavy, positive alpha particles at a super thin sheet of gold foil. Now, if the watermelon model was right, these heavy particles should have just blasted straight through, like bullets through tissue paper. And yeah, most of them did just pass right through the empty space. But to everyone's absolute shock, a few of them were deflected at really sharp angles.
The key takeaway here is this staggering number, 1 in 20,000. That is how incredibly rare it was for an alpha particle to not just deflect, but basically bounce straight back at the source. Rutherford himself literally compared it to firing a 15-inch naval shell at a piece of tissue paper and having it bounce back to hit you. No way, right? This enormous repulsive force meant the positive charge couldn't be spread out like a watermelon. It had to be crammed into a ridiculously tiny, dense center. And that is what Rutherford famously named the nucleus.
Let's just compare these two models for a second. Thomson gave us this solid, immovable, positive sphere. But Rutherford, he presented this radical new idea that the atom is almost completely empty space. To put that into perspective, the whole atom is about 10 to the negative 10 meters wide, but the nucleus is 10 to the negative 15 meters. If the atom was the size of a giant football stadium, the nucleus would be the size of a single pea sitting right on the 50-yard line, yet it contains almost all of the atom's mass.
Which brings us to our next hurdle, Section 3, the collapsing atom paradox.
Okay, so Rutherford solved the scattering mystery, but remember that relay race we talked about? He unwittingly handed off a fatal flaw that caused a literal crisis in classical physics. See, according to Maxwell's proven electromagnetic theory, any charged particle that accelerates must emit electromagnetic radiation, and Rutherford's negative electrons were revolving in circles around the nucleus. Even if their speed is steady, going in a circle means your direction is constantly changing, which means you are constantly accelerating. So by the strict rules of classical physics, these orbiting electrons should be continuously radiating and bleeding off energy.
And here's the paradox. If they're losing energy, their orbits have to shrink. The math showed that an electron would spiral into the nucleus actually, scratch that, it wouldn't even be a slow spiral. It would crash in about 10 to the negative 8 seconds.
a tiny fraction of a millisecond. If Rutherford's model and classical physics were both 100% right, atoms would collapse instantly. The screen you're looking at, your own body, matter literally shouldn't even exist.
So somebody had to fix this. Section 4. Bohr's quantum leap?
Enter Niels Bohr in 1913. He looks at this paradox and realizes that to save the atom, he has to just break the rules. Classical physics was clearly broken at the microscopic level, so Bohr creates these revolutionary new postulates. First, he says electrons revolve in fixed, allowed circular lanes. He called them stationary orbits. Second, and this is the crazy part, he said that in these specific orbits, electrons simply do not radiate energy. He literally just hit pause on Maxwell's laws. He said energy is only emitted or absorbed when an electron physically jumps, a literal quantum leap, from one orbit to another. Finally, he stated that the angular momentum of the electron is strictly quantized. It could only be whole multiples of Planck's constant divided by 2 pi. They couldn't just exist anywhere, they had to stay in their specific lanes.
If we look at how Bohr balanced the forces, it's actually super elegant. Once you restrict the electron to its allowed lane, the mechanics work perfectly. The inward Coulomb force, that's the electrical pull drawing the negative electron to the positive nucleus, is perfectly balanced by the outward centrifugal force from its rotation. As long as the electron stays in that allowed, quantized orbit, the whole system is completely stable.
But the story doesn't end there. Section 5. The quantum mechanical cloud.
Bohr's model was a total game changer, especially for explaining the hydrogen spectrum. But as scientists kept digging, they realized that even his neat little planetary orbits weren't the real truth. When we look at Bohr's classical orbits versus the new quantum mechanics dreamed up by Schrödinger and Heisenberg in 1926, the idea of absolute certainty just vanishes. Heisenberg's uncertainty principle basically said you cannot know both the exact position and the exact velocity of an electron at the same time. The harder you try to pin down where it is, the less you know about where it's going. So mapping a perfect orbit is impossible. We have to trade absolute certainty for mere probability.
I love how the legendary physicist Richard Feynman summed this up. He said, "We cannot therefore properly speak of the electron moving in some orbit around the proton. The most we can say is that there is a certain chance of observing the electron." So the true picture of an atom isn't a cute little miniature solar system. Because electrons have wave-like properties, they're much better described as confined waves, or these three-dimensional hazy clouds of probability where you might just find an electron.
And that brings us to one final mind-bending thought. Look around the room right now. The solid desk you're sitting at, the phone in your hand, your own body. It's all made of atoms. And as we've explored today, those atomic models are almost entirely empty space, governed at their core by nothing more than hazy clouds of mathematical probability. If the most fundamental building blocks of our universe aren't solid little spheres but ghostly waves of chance, what does that actually mean for our definition of reality? I'll leave you to ponder that one. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I will see you in the next one right here on my channel, JEE Concept Galaxy.